Today we're going to be continuing with number theory and methods of proof. Direct proof and counterexample 4 with about divisibility. And when you were first introduced to the concept of division in elementary school, you were taught that 12 divided by 3 is 4, because if you separate 12 objects into groups of 3, you get 4 groups with nothing left over. You may have been taught that to describe this fact by saying that 12 is evenly divisible by 3, or 3 divides 12 evenly. I don't know if I agree with this statement, but the notion of divisibility is the central concept of one of the most beautiful subjects in advanced mathematics. I don't know if I'd use the word beautiful, but whatever. Number theory, the study of the properties of integers. Definition: if n and d are integers, then n is divisible by d if and only if n equals d times some integer and d does not equal 0. You could also say n is a multiple of d, n is a factor, or d is a factor of n, d is a divisor of n, or d divides n. The notation d pipe n reads d divides n. Symbolically, if n and d are integers, d divides n if and only if there exists an integer, say k, such that n equals dk and d does not equal 0. This notation reads as d does not divide n, the pipe with the slash through it. So all these, 21 divisible by 3? Yeah, because 3 times 7 is 21. Does 5 divide 40? Yeah, 8 times 5 is 40. Does 7 divide 42? Yes. 42 equals 6 times 7. Is 32 a multiple of negative 16? Yeah. A negative 2 multiple. Is 6 a factor of 54? Yeah, because it divides 54 evenly. Is 7 a factor of negative 7? Yeah, because it's a multiply it by negative 1, which is also an integer, and you get negative 7. So it's yes to all of the above. If k is any non-zero integer, does k divide 0? Yeah. Because 0 times k is 0. So yes, k does divide 0. Two useful properties of divisibility are that if one positive integer divides a second positive integer, then the first is less than or equal to the second. And the only divisors of 1 are 1 and minus 1. So those are theorems 4.4.1 and 4.4.2. If a and b are integers, is 3a plus 3b divisible by 3? Yeah, you can factor out the 3 and divide by 3, and you're left with a and b, which is an integer, because the sum of integers is an integer. If k and m are integers, is 10km divisible by 5? Yeah. You get 2km, which is also an integer, so because k and m are integers. This first one by the distributive law of algebra, and the second one by the associative law of algebra. When the definition of divides is rewritten formally, it is using the existential quantifier. Since the negation of an existential statement is universal, it follows that D does not divide N if and only if, for all integers k, N does not equal dk, or D equals 0. In other words, the quotient N over D is not an integer. Does 4 divide 15? Because the quotient isn't an integer. So no. An alternative way to define a prime number is to say that an integer n greater than 1 is prime if and only if its only positive integer divisors are 1 and itself. So, proving properties of divisibility. Prove that for all integers a, b, and c, if a divides b and b divides c, then a divides c. So, it's already written informally, so you can immediately pick out the starting point, and the conclusion must be shown. That must be shown. Starting point. Suppose a, b, and c are particular but arbitrarily chosen integers such that a divides b and b divides c. Show that a divides c. We need to show that c equals a times some integer. So, since a divides b, then b equals ar. Since b divides c, c equals b times s. So you can substitute ar for b here, and you'll get c in terms of a. By the associative law, you can isolate the a, and then just show that rs is an integer because multiplication of integers is closed. So c equals a times some integer. Therefore, c is divisible by a. So that's the transitivity of divisibility theorem. For all integers a, b, and c, if a divides b and b divides c, then a divides c. Divisibility by a prime. Didn't show this, but as a proof, but it's any integer n greater than 1 is divisible by a prime number. Either itself or it, we'll show later, the product of primes. Counterexamples and divisibility. Is the following statement true or false? For all integers a and b, if a divides b and b divides a, then A equals B. Okay? So the statement is false. All you need to do is come up with a counterexample. The following discussion describes a mental process that may just take a few seconds. May be useful to use consciously, however, to solve more difficult problems. First off, you would start off with what you, as if you were trying to prove what that this is true. So starting point, suppose A and B are integers such that A divides B and B divides A. Must it follow that A equals B, or could it happen that A does not equal B for some A and B? Focus on the supposition. Definition of divisibility means B equals HA and A equals KB for some integers K and H and K. If you do substitution, you get B equals HA, which equals HKB, or HKB. Since B cannot be equal to 0 because B divides A, you could divide both sides by B, and which leaves you to minus 1 equals HK. And H and K are divisors of 1. But by theorem 4.4.2, the only divisors of 1 are 1 and minus 1. Thus, H and K are both 1 or both are minus 1. If H equals K equals 1, then B equals A. But if H equals K equals minus 1, then B equals minus A. So A does not equal to B. This suggests you can find a counterexample by taking B equals minus A. The formal answer would be the statement, the counterexample, and the conclusion. So, the unique factorization of integers theorem. Let's see here. Yeah. The most comprehensive statement about divisibility of integers is contained in the unique factorization of integers problem, or theorem. It's important, so sometimes called the fundamental theorem of arithmetic. The unique factorization of integers theorem says that any integer greater than 1 is either a prime or can be written as a product of prime numbers in a way that is unique, except for perhaps the order for which in which the primes are written. Example: 72 equals 2 times 2 times 2 times 3 times 3. And you can change the order, and as long as the number of 2's and the number of 3's is consistent, it will always equal to 72. No other collection of prime numbers besides 3 2's and 2 3's multiplies out to 72. Unique factorization of integers theorem. Given any integer n greater than 1, there exists a positive integer k, distinct prime numbers p1, p2, p3, so on and so forth to pk, and positive integers e1, e2, e3 to ek, such that n equals p1 to the e1 power times p2 to the e2 power, and so forth to pk to the ek power. And any other expression for n as a product of prime numbers is identical to this, except for the order, perhaps the order in which the factors are written. The standard factored form has the prime numbers ordered from low to high, going from left to right, such that P1 is less than P2, which is less than P3, and so forth, less than Pk. Write 3300 in standard factored form. What would that be? $3,300 equals 33 times 100. 100 equals 10 times 10. 10 times 10 is 2 times 5 times 2 times 5. 33 is 11 times 3, which are prime factors. So you're left with times what? Yes, but in standard factored form, it would be 2 squared times 3 times 5 squared times 11. You order the factors, the prime factors, in ascending order. So, yeah. That's what you get. Now suppose m is an integer such that this is true. Eight times 7 times 6 times 5 times 4 times 3 times 2 times m equals what's on the right there. Does 17 divide m? And if so, why? Why not? We don't know what m is, so. Well, 17 is a prime, so it is a prime factor on both sides of the equation because they're equal, right? But 17 is greater than these numbers here, so it must be a prime factor of m. Therefore, 17 divides m. Make sense? Kind of, sort of? I think they might explain it a little bit better. Since 17 is one of the prime factors on the right side of the equation, it is also a prime factor on the left side of the left side. But as 17 does not equal any prime factor of 8, 7, 6, 5, 4, 3, or 2, because it's too large, hence 17 must occur as one of the prime factors of m. So 17 divides m. And that is it for divisibility. Continuing on with number theory and methods of proof. Direct proof and counterexample 4, division into cases and the quotient remainder theorem. And we'll start off with the quotient and remainder theorem, which states given any integer n and positive integer d, there exist unique integers q and r such that n equals dq plus r, and r is greater than or equal to 0 but less than d. In number line form, you can see that n is d times some integer q plus r. Division into cases. If n is negative, the picture changes. Since n equals dq plus r, where r is non-negative, d must be multiplied by a negative integer q to bring dq either exactly to n or a point below n on the number line, so that a positive integer r can be added to qd. So let's take the example of b. If so, n minus 54 equals 4q plus r. Can you find a value for q? And r? Q has to be a negative number, and 4q has to be greater than or equal to, or less than or equal to negative 54. But then r would be greater than d, greater than 4. R can't be greater than 4. See? Again, r would be greater than d, greater than 4. Negative 15? Yeah, but then it would be negative 60 plus r, so 6 is r would have to be 6, which is greater than 4. So the correct value would be q equals negative 14, making it negative 54 equals negative 56 plus r. Add 56 to both sides, and you end up with 2 equals r. Right? So you're just below the 54, so that r does not exceed the d value. All right? No, don't do this to me. You did it to me. All right, so yeah, minus 4 equals 4 times negative 14 equals negative 56, plus 2 equals negative 54. Div and mod functions. Given an integer n and a positive integer d, n divides d, div d, is the integer quotient obtained when n is divided by d. This is what a lot of programming languages do when you do integer division. They don't give you a float afterward, or a float or a double as a response. They give you the integer division value. The n mod d is the non-negative integer remainder obtained when n is divided by d. Symbolically, if n and d are integers and d is greater than 0, then n div d equals q and n div mod d equals r, such that if and only if n equals dq plus r, where q and r are integers and r is greater than or equal to 0, but less than d. Compute 32 div 9 and 32 mod 9 by hand. Okay. Five. Yes. 3 and 5. Obtained by a long division here. To compute n mod d, substitute n div d in place of q and d, q and n mod d in place of r in the equation. N equals dq plus r. The result is n equals d times n div d plus n mod d. Solving for n mod d gives you n minus d times n div d equals n mod d. Like I said at the beginning of the semester, this is formalized common sense. This is stuff you learned in 7th grade or I'm sorry, 4th or 5th grade, long time ago, and just coming back to haunt you. Okay. Suppose m is an integer. If m mod 11 equals 6, what is 4m mod 11? No, I'll skip over proof for A. Okay, because m mod 11 equals 6, the remainder when obtained when m is divided by 11 is 6. This means that there's some integer q such that so that m equals 11q plus 6. Thus, 4m equals 44q plus 24, which equals 44q plus 22 plus 2, which equals 4q plus 2 plus 2. Since 4q plus 2 is an integer, because products and sums of integers are integers, and since 11 is less than 2 is less than 11, the remainder of obtained when 4m is divided by 11 is 2. So, yeah, you factor out the 11 from these two items here to get that, and it resembles this, except for the plus 2. And then you get 4m mod 11 equals 2. Representations of integers. We defined an even integer to have the form twice some integer. At that time, we could have defined an odd integer as one that is not even. The fact that any integer is either even or odd is called the parity property. Prove that given any two consecutive integers, one is even and the other is odd. Okay, so what does consecutive mean? It means one is one more than the other. So if one integer is m, the next consecutive integer is m plus 1. To prove the given statement, you can divide the analysis into two cases. One, where the smaller of the two integers is even, and number two, where the smaller of the two integers is odd. So, in this case, m equals 2k for some integer k, so that m plus 1 equals 2k plus 1, which is odd by definition of odd. And so in this case, one of m and m plus 1 is even and the other is odd. The other case, m is odd, which means m equals 2k plus 1 for some integer k, so m plus 1 equals 2k plus 1, which equals to 2k plus 2, which equals 2 quantity times the quantity k plus 1. But k plus 1 is an integer, therefore m plus 1 equals twice some integer, and thus m plus 1 is even. Therefore, in this case also, one of m and m plus 1 is even and the other is odd. So that was what we were trying to show. So theorem 4.5.2 is that any two consecutive integers have opposite parity. To prove a statement of the form, if A1 or A2 or yada 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 to AN, then C, prove all of the following. If A1, then C. If A2, then C. And so forth to if AN, then C. This process shows that C is true regardless of which of the A's happens to be the case. That's a proof by division into cases. Show that any integer can be written in one of the four forms. N equals 4q, or 4q plus 1, or 4q plus 2, or 4q plus 3, for some integer q. Well, given any integer n, apply the quotient remainder theorem to n with a divisor equal to 4. This implies that there exists an integer quotient q and a remainder r such that n equals 4q plus r. And r is greater than or equal to 0, but less than 4. The only numbers that satisfy this, or the only integers that satisfy this, are 0, 1, 2, and 3. Therefore, one of those equations applies for some integer q, because n mod 4 equals 0, 1, 2, 3, or 3. Write this one down, because this is going to be homework due next Tuesday. We're going to look at some possibilities for how to go about this. But the square of any odd integer has the form of 8m plus 1 for some integer m. So, how would you go about doing that? Formal restatement, first of all. What do I need to show? And is where you start from. And then what do you need to show? Formal restatement is for all odd integers n, there exists an integer m such that n squared equals 8m plus 1. Starting point, suppose n is a particular but arbitrarily chosen odd number. Show there exists an integer m such that n squared equals 8m plus 1. Why should there be an integer that satisfies that? That would say that n squared minus 1 is divisible by 8. Perhaps you could make the use of the fact that n squared minus 1 equals n minus 1 times n plus 1. Does 8 divide n plus 1, it's a typo, times n minus 1? Since n is odd, both n minus 1 and n plus 1 are even. This means that their product is divisible by 4, but that's not enough. You need to show that the product is divisible by 8. You could try another approach, arguing that since n is odd, you can represent it as 2q plus 1 for some integer q. Then you can expand that out and show that 4 times the quantity q squared plus q plus 1 is divisible, can be written in the form of 8m plus 1. Yet another possibility is to use the result of 4.5.6. That example showed that any integer can be written in one of 4 forms. And the 4q plus 1, 4q plus 2, 4q plus 3. 2 of these are 4q plus 1 and 4q plus 3 are odd. Thus, any odd integer can be written in the form of 4q plus 1 or 4q plus 3 for some integer q. You could try breaking into classes based on these 2 different forms. It is true, it is possible to prove this, but I'm going to, like I said, leave it to you for homework. Due, like I said, next Tuesday before class. I'll put it on Canvas. You can submit by Canvas or by paper. Either way. Either way is acceptable. Absolute value and the triangle inequality. Well, triangle inequality is one of the most important results involving the absolute value. It has applications in many areas of mathematics. For any real number x, the absolute value of x, denoted by this, is defined as follows. The absolute value of x equals x if x is greater than or equal to 0, and minus x if x is less than 0. Basic algebra, I think, for that one. But just a reminder. But for every real number r, the negative of the absolute value of r is less than or equal to r, which is less than or equal to the absolute value of r. For every real number r, the absolute value of negative r equals the absolute value of r. And the triangle inequality for all real numbers x and y, the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. Doesn't get into proofs or anything like that on those, just throwing those out there to so you could use them in proofs for later use them in later proofs. I believe that's it for the slides for the day. So remember, homework for Tuesday gives you a week to work on it. Give you some practice writing out proofs in coherent form. And I guess I will see you on Thursday.